In this video, we're covering integration involving logarithmic functions. So on your screen there, you can see our first rule, and we have the integral of 1 over x dx equals the natural log, or ln, of the absolute value of x plus c. Now, the absolute value of x just means that if we have a negative, it has to come out as a positive. Alright, so if we begin, we'll have an example here. Evaluate the integral from 1 to 5 for 3 over x dx. So the first thing we need to do is use our formula, which is up above, to convert it into its antiderivative. So if we have 5, 1, we know this is going to convert to using our formula up here. We're going to change this to 3 comes out the front, because 1 over x turns into ln x. So if we have a constant on such as 3, it just stays as 3. ln x, and on the side we have 5, 1. Now remember, when you're doing your integrals, it's your biggest number, so the 5 in this case, subtract the small number. So in our case, we're going to get 3 natural log 5. That's our first one, and then we're going to subtract the second one. So our bigger number, the 5, came first, and then the smaller number comes second. So here, our 3 ln 5 is going to remain as 3 ln 5. ln 1, if you remember, so ln 1 equals 0. So we can say that this is going to be 3 times 0. And 3 times 0 is 0. So our 3 ln 5 is our final answer. The next thing we're going to look at is another version where you have two functions. So the integral of the derivative on top over the original function dx. So here we know our function on the bottom, our fx, equals x cubed plus 7. So if I differentiate that, I get 3x squared. Alright. The problem is, in our original integral, we have x squared on top instead of 3x squared. Alright, so we need to somehow manipulate the fraction to get our 3x squared on top. So if I decide I wanted to add the 3, so here we've got this is what we have, and we want to get to something different. So if I have this, but that x squared I want to convert to 3x squared, I can't just put the 3 there. So what I need to do is I need to have 1 over 3. So the integral is going to be 1 over 3. Now I can have my 3 at the top there. X squared over x cubed plus 7. And there's a little times in between there. Alright. Because I've added the 3 over here, I need to make sure that I've got the 1 over 3, which essentially will cancel it out to get me back to the original that we were given. Alright. So because we have a 1 over 3 out the front in red, that counts as being a constant, so we can factorize that out the front, and we get 3x squared over x 3 plus 7 dx, which now fits our derivative over the original function. Alright, so now that we've got that, we've got 1 over 3, and then we can use our formula up here, which is ln the original function. So ln the original function, which was x cubed plus 7 plus c. Alright, so it's important to note that you do have to do some manipulation here. We didn't have the antiderivative on top, so we need to manipulate the fraction or the equation to get that, and that involved adding a 1 over 3 out the front. So we're going to look at some more examples now. Alright, in this one we're going to find the integral of the function, so that means we're going to find our integral of 2x plus 5. Now I've got a function on the bottom, so that means I'm going to be using the integral of my derivative over here equals ln x plus c. Alright, we'll put the dx in there and a dx there. Alright, so we need to make sure that this fits into that. So my original function, my fx, was 2x plus 5. If I differentiate that, I get 2, which is good. That means I don't need to do any manipulation like I did in the previous example. I can simply just plug and play here. So we can go straight to using that formula up there. So the integral of 2 over 2x plus 5 dx is going to equal ln, the absolute value of 2x plus 5 plus c. Now remember, you always need that c at the end there. So we're going to look at another one now. Alright, so we're trying to find the integral of this over 2x 6 plus 5 dx. So my original function is my denominator, so 2x 6 plus 5. If I differentiate that, I get 12x to the power of 5. Now, unfortunately, that's not what's on top, so we do need to do some manipulation here. So what I need to do is I need to make sure my integral here, if I'm adding the 12 to the top, I need to make sure I have the fraction of 1 over 12 out the front. Over 5 over 2x 6 plus 5 dx. So that is a constant. Our 1 over 12 here is a constant, so it can come out the front. And then we're finding the integral of 12x5 over 2x to the power of 6 plus 5 dx. And that matches our integral of the derivative over the function. And we know that changes into ln, the absolute value of x plus c. So knowing that, we get 1 over 12 here, and then we get ln, the absolute value of 2x to the power of 6 plus 5, and plus c at the end. So now we're going to use our definite integrals. And this follows pretty much the exact same thing we've been doing this whole time. So I know that my fx is going to equal 2x squared plus x plus 1. So if I differentiate that, I get 4x plus 1, which happens to be what's on top. So again, lucky, we don't have to do any manipulation here. So I can go the integral of 4x plus 1 over 2x squared plus x plus 1 dx goes to the absolute value of our function, which is on the bottom, our denominator. But we've got to make sure, because we're doing a definite integral, we have the 3 and the 0 here. Now remember, your highest number goes first. So down here, we're going to have the natural log of 2 times 3 squared plus 3 plus 1, because that was our larger of the two, minus 2 times 0 squared plus 0 plus 1. Now, if you put that in the calculator, you'll end up with 3.1. So at the end of the video, we'll do a recap. So on your screen, you can see your two formula that we used throughout the video. Remember, with the second one, when you're dealing with functions, there are times when you need to do some manipulation, which means you're trying to find the derivative that matches what you're getting when you differentiate that original one. For example, when we had this example here, the top up here, our numerator, did not match our first derivative. So we needed to add the 1 over 12 to allow us to continue with using the formula in red down the bottom.